Namaste and welcome back to JEE Chemistry with Typical Monk. This is class 37, the D and F block elements. The heart of the periodic table belongs to the transition and inner transition metals. The D block, groups 3 to 12, and the F block, the lanthanides and actinides set apart at the foot of the table. What unites them is a partly filled inner shell of D or F orbitals, and from that single fact flows a rich chemistry. Variable oxidation states because the d electrons are so close in energy, vivid colors from d to d electronic transitions, paramagnetism from unpaired electrons, and a gift for catalysis and complex formation. Among the F block, the lanthanides show a slow, relentless shrinking called the lanthanide contraction, which leaves later elements almost identical in size. Learn the properties, the causes of color and magnetism, and the contraction, and this becomes one of inorganic chemistry's most rewarding chapters. Today, the D and F block elements, one idea at a time. Here is what you will master today. First, the position of the D and F block. Second, the characteristic properties. Third, the variable oxidation states and color. Fourth, the lanthanides and the contraction. And fifth, the actinides, one idea at a time. Let us set the foundation. The D block, the transition elements, groups 3 to 12. The F block, the inner transition elements, the lanthanides and the actinides. The signature, a partly filled set of d odd orbitals. Mass align, partly filled inner orbitals give color, magnetism, and variety. Now look at the picture. The blocks of the periodic table. The D block, the transition metals, groups 3 to 12 in the middle. The F block, the inner transition metals set apart at the bottom. The lanthanides, the 4 series, and the actinides, the 5 series. The defining feature, a partly filled D or F subshell. Now, the hallmarks of the transition metals. Variable states. Many oxidation states, the d electrons are close in energy. Colored ions from d to d electronic transitions. Paramagnetism from unpaired d electrons. And more. Catalysis, alloys, and complexes, the hallmarks of the transition metals. Now why they vary and why they glow. Variable states. Many oxidation states, often differing by 1. The highest, reached in the middle of a series, like manganese, +7. Color. From D to D transitions, the ion shows the complement of the color it absorbs. Magnetic moment. The root of n times n plus 2 in bored magnetons. The key compounds, potassium permanganate and potassium dichromate. Now look at the picture. The lanthanide contraction. Lanthanide contraction. A steady decrease in size across the 4 series. The cause. The 4 electrons shield the nucleus poorly. The effect. Zirconium and hafnium end up nearly the same size. The consequence. It makes the lanthanides hard to separate. Now, the lanthanides in full. The lanthanides. The 4 series, cerium to lutetium. Lanthanide contraction. A steady decrease in size across the series. The cause. Poor shielding of the nucleus by the 4 electrons. The effect. Zirconium and hafnium end up nearly the same size. It makes the lanthanides hard to separate. Now, the actinides. The actinides. The 5F series, and all of them are radioactive. More states. They show more oxidation states than the lanthanides. Actinoid contraction, like the lanthanide contraction, but greater. Now match each feature to its family. A partly filled D subshell goes to a transition element. Colored ions go to D transitions. The 4F series goes to the lanthanides. And the 5F series goes to the actinides. 4 pairs, each worth memorizing. Now, how many of these statements are correct? Statement 1. The transition metals show variable oxidation states. Correct. Statement 2. The color comes from ester sessions. Wrong. It comes from D to D transitions. Statement 3. Lanthanide contraction is a decrease in size across the series. Correct? So the answer 2 are correct. Statements 1 and 3. The trap is the kind of transition in statement 2. Now, the 2 mistakes that quietly cost marks. The truth, the color in transition ions comes from D to D transitions. In the trap, calling zinc a typical transition element, its D subshell is full. The second truth, the lanthanide contraction makes zirconium and hafnium almost identical in size. The second trap, forgetting that the actinides are all radioactive. Now test yourself. Answer in your head before the reveal. That is how G-speed is built. Here we go. Question 1. The D block groups 3 to 12. Question 2. The cause of color D to D transitions. Question 3. The magnetic moment formula, the root of n times n plus 2. Question 4. The 4-phase series, the lanthanides. And question 5. The 5F series, the actinides. Let us gather it all in one breath. The D block is the transition, the F block, the inner transition. Variable oxidation states, color, paramagnetism, and catalysis. Color from D to D transitions. The moment is the root of n times n plus 2. Lanthanide contraction. Size falls across the series. The actinides, radioactive with more oxidation states. Next class, metallurgy, the extraction of metals. Color, magnetism, and variety. The transition and inner transition metals are the most versatile citizens of the periodic table, and a single idea explains them all, a partly filled inner shell. Because the d electrons lie so close in energy, these metals wear many oxidation states. Because those same electrons can jump from one d orbital to another, their ions glow with color, and because some stay unpaired, the metals are paramagnetic and become catalysts, alloys, and the hearts of countless complexes. Below them, the lanthanides shrink quietly across their row, the lanthanide contraction, leaving zirconium and hafnium almost twins, while the radioactive actinides push the same ideas further still. Learn the properties, the origin of color and magnetism, and the contraction. And this chapter turns into reliable marks. Next class, metallurgy. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time. You will crack G. I will see you in the next class.